Okay. Hi, everyone. Welcome to the open problem session. So it's my pleasure to host this session today, and I'm very happy to do so. That's always been one of my favorite sessions at Beyond IID. And for now, we have a couple of speakers who have agreed advance of time to say something at the session. But I also want to say that I guess more or less like in the usual open problem session, you're very welcome to just come up and let me know if you want to also contribute something spontaneously. And I'll be checking the chat, but also the Slack, in case you want to ask any questions about the presentations. And first, I think we start with Daniel.
Christoph, I need 1 minute because I have a technical problem. I thought I could share my iPad screen, but I need a cable to do that. So
Sure.
Maybe if you give me one minute to just export the PDF of my presentation to my computer. Sorry about that.
No worries. Then can we switch order? Navneet, are you already prepared if we switch order?
Yeah.
Perfect. Then we start with the second. So Navneet has an open problem to present. I think you can just go ahead and, I don't know, maybe share your screen if you have something.
Hey, do you see my PowerPoint?
Yeah, now I see your PowerPoint. Perfect.
Cool. Yeah, maybe I will just say something quickly about the background for those who didn't attend the talk yesterday. But I'm working on quantum state splitting, and here the task is that, well, Alice holds this quantum state with two registers A and A1, and the purification of this is on R, and she would like to send this A1 register to Bob. And to do so, they have access to some pre-shared resource state, such as free entanglement, for example, and then Alice applies an encoder, and the output of that is A and Q is the register that goes across to Bob. And so the state at the end of it, rho tilde, hopefully is close in purified distance to rho. And we would like to minimize the communication cost, which is the log of the dimension of Q. And when we do so, we obtain a result in terms of the partially smoothed max information. So yeah, here's I guess people are familiar with the max relative entropy and the max information. And the smooth max information is just a minimization of the max information over all the rho bars in an epsilon ball around rho. And the partially smoothed one has this additional condition that the marginal of rho bar A is the same as rho A. So this is the result that we have. And what we did was now look at this for rho tensor n, so n IID copies of rho. And there we looked in particular at the moderate deviation regime. So we asked that the error epsilon will be e to the minus n an squared for a moderate sequence an. And then it turns out that the communication cost for state splitting is given by this expression. So this works if we choose the error to be this way. And I guess the open problem that I would like to now present is when this kind of expansion doesn't work. So before I do that, so I can just tell you quickly where I think the problem is. I think the problem is in the achievability part of this theorem. So although I can't be sure of that, but today at least let's only look at the achievability part and maybe see how that goes. So how it goes is, so we have the partially smoothed max information, and the first result that we use is we bound it by the smoothed max information. And the best we can do is actually make this ball half the size of this ball. So if we do that, then we have this upper bound. And then the smooth max information is a minimization over all of these states. So we just choose one particular state, rho r tensor n. And then we have a Dmax as a smoothed Dmax here. And then we upper bound that with a hypothesis testing relative entropy. And for the hypothesis testing relative entropy, it turns out that you have this kind of expansion. So if you have a 1 minus poly n en, where this is of this form, then you have this expansion here. So these were the steps that we had to use. And the converse result that we have is essentially this third line, but for any k larger than or equal to 1. And notice that because we're in the moderate deviation regime, this poly n factor doesn't matter. So you can have whatever you want here. So we have this 1/4 here, for example, but it doesn't change the result. The right-hand side is the same. So that's why we're able to get a matching achievability and converse. So the cases where this does not work, for instance, is the second order result. So if we have a fixed epsilon, then the hypothesis testing relative entropy has this expansion. And so you have this phi inverse of epsilon. So this is the inverse of the CDF Gaussian. And so clearly, if you have two different prefactors, so here, for example, you have this 1/4, and here you have some k, which is larger than or equal to 1. So then you will get different achievability and converse results. So you have a gap there. So that's one case where it fails. Another case where we have a problem is where epsilon is large. So we would also look at moderate deviation, but with large error, so of this form. And here again, we have problems because notice that here essentially you reduce the ball by a factor of 1/2. So the goal there would have been to get to a hypothesis testing relative entropy with just epsilon squared, but instead we will get like a 1/4 here, so 1 minus 1/4, so you'd get like a 3/4 up here. So that also doesn't work very well. And lastly, I can say one more thing. I'm not sure how closely these things are connected, but I will just say them anyway. So the last thing is to look at channel simulation. So the idea of channel simulation is if Alice and Bob wanted to simulate a channel, one way to do that is just that Alice just simulates the channel locally, completely on her side. And then whatever output she gets, she state splits that, right? And so this is one way of achieving channel simulation. There's a Definetti reduction argument that essentially says that if you can do state splitting with some error, then you will have channel simulation done with the error scaling by a polynomial factor. So once again, this poly n factor doesn't hurt us in the moderate deviation setting. But if you look at, for example, large error like this, then we don't even know how to do state splitting anymore because essentially of this problem here. So the question really, I think, that might have a good answer is, can we bound the partially smoothed max information with the smooth max information, but do better than this kind of halving of the ball? Yeah. Does that make sense, or maybe can explain some parts better? Sorry, I'm gonna.
We do have plenty of time, actually, if you want to say anything more, but I think it made sense overall.
Yeah, okay, maybe I can say that this proof actually is taken from this paper. Yeah, this paper here. This is partially smooth information measures by these authors. And the theorem in question here is find it now. Yeah, here it is. So theorem 2, which essentially does this. So it's kind of a quite an interesting proof that they go through here, but essentially, yeah, you have to construct. So you start with the state that achieves the optimization on the right-hand side, and from that state you construct one that also does it for the left-hand side, and then you show that the state on the left is in this 2 epsilon plus delta ball. And so I guess it would be nice if we could show that the distance of that state that you constructed that achieves the left-hand side is closer than 2 epsilon times delta. Hopefully it's in some epsilon times delta ball. Yeah, and especially this makes sense for large error, right? So if this epsilon is close to 1, then it doesn't make sense that I should have to go, yeah, essentially to 1 to find a state that is achieving it. Yeah.
Okay, thank you. We can check for a second if there are any questions coming up. But can I ask you? I was wondering generally, you use always these partially smooth quantities, and then you bound them by more or less the same quantity in the non-smooth regime, right? Is there also some way to approach these proofs by just continuing? I don't know if that makes sense, but continuing with something that's like partially smooth and not loose by going back to like a fully smooth quantity.
I mean, that might be possible. So the part then that you would hope for is some kind of relationship between, I guess, a partially smoothed version of this max relative entropy
like that, yeah.
and the hypothesis testing relative entropy. So yeah, that might be also a way to sidestep this problem, essentially, by avoiding the smoothed quantity altogether.
Okay. But
Yeah.
nothing in that direction is known, like a partially smoothed relative entropy or max relative entropy.
To the best of my knowledge, no, but yeah, but perhaps someone in the audience knows if there's such a connection between partially smooth max relative entropy and the hypothesis testing relative entropy.
Okay, thank you. I don't see any other questions right now.
Chris, I think there's someone raised their
I see Joe. Yeah, go ahead.
Yeah, so I'm not sure if this would impact your question, but a little while ago, Dina and Hadi and I looked at a compression problem, just pure, just compression, and we were in the course of that the second order behavior for the partially smoothed entropy at least depends on the state. Like the epsilon, the epsilon dependence depends on the state. So I'm not sure how easy it will be to make. You were just saying like well, we could get this better where instead of the 2 just have epsilon minus delta. I have a feeling that might imply that somehow the second order behavior would be this almost the same as the. Anyway, I'm just that's my immediate reaction. And Chen send you the link if you want.
Yeah, thanks. Sorry, I was muted there. But yeah, I think I know the paper you're talking about. I also thought maybe I could find something there, but yeah, maybe I should have a closer look at that now that this is done. So yeah, thanks.
Just wanted to mention. All right.
Okay, are there any other comments? Otherwise, I think we can maybe go to the next problem. Yeah,
So
thanks, Navneet.
Thanks.
Not sure how it works in this app. Maybe Navneet, you need to stop sharing your screen and then Daniel can share your screen.
Okay.
Perfect.
So thanks, and sorry for this. Can you see my screen now? Yeah. So sorry for this. The triple embarrassment. So first I wrote publicly in the chat when I wanted to just talk to Christoph, and that not only that, you could see that I was lying because I told him everything was okay when in fact I had a technical issue, and I also apologize for the technical issue, but I think everything should be fine now. And well, so what I wanted to talk is just this the following problem. So probably most in the audience know. Oops. Sorry, most of the audience know about recoverability bounds. So let me start by some very basic stuff, namely the data processing inequality, which you probably also already know by heart. So we're just given some quantum channels, some states, and we know that the relative entropy contracts if we apply to channels to it. And in many problems, and actually one of my favorite questions is how can we actually refine the statement, how we can actually obtain improved versions of the statement that the relative entropy contracts. And one possible refinement of the data processing inequality are so-called recoverability bounds. And they are of the following form. So we are given, there's some reference state sigma, and then there is another quantum channel R sigma, which goes from the image of the previous quantum channel to its domain. And it has the property that when we apply this channel to the state sigma itself, we recover sigma. And usually recoverability bounds are of the form, by the way, can you see my mouse? I'm not so familiar with this app.
Yeah, I can see.
Okay, cool, thanks. Yeah, so they're usually of the form like that you take the relative entropy before applying the map minus the relative entropy after you apply the channel, and you want to show that it's lower bounded by some function that depends on your initial state and what happens when you apply this recovery channel to the state after you apply the channel. And this is has to be like a strictly positive, like not strictly, sorry, positive or equal to zero quantity, which then, of course, if you just plug the fact that this is greater or equal to zero, you recover the inequality in the left. And there is a lot of literature on it. This was, I think, quite a popular problem a few years ago. And as far as I know, I think the best, well, there are many subtleties there, usually whether on this map is universal or not, but I mean, can depend on the state rho or not. But as far as I know, the best you can do, as we know, is to take this function to be the measured relative entropy, but if you want some other nicer properties of this map are, I think, log fidelity or something, but that's not really, well, so for some reason this isn't appearing like the explicit form of this R map, but it also isn't very important. But yeah, so of course these results are very nice, but I was wondering if one can also derive multiplicative versions of these inequalities. And by that, I mean that instead of looking at the difference between these two channels, like these two relative entropies, one actually considers their ratio. So you want like to get this should be an inequality in the other direction, sorry. And so you want to really upper bound this ratio here in terms of properties of the recovery map. And why would that be interesting? Well, in principle, these inequalities, if you can have the ratio, they are a bit stronger than the ones if you have the difference of the two relative entropies, because you can iterate then this procedure, and for some applications, this sort of contraction quantified by this ratio is more relevant than this difference. And I'm not even aware classically of results like this where you're allowed to consider like how well the map recovers after applying the state, after applying the channel. So yeah, I would be interested in knowing if anything can be said in this direction. And I don't even, unfortunately, have concrete suggestions as to how this inequality should look like, but I would be interested to see something like that. So yeah, that's the problem.
Hi, Daniel, can you give me just a little more motivation? I mean, for the usefulness, you said, for instance, can be iterated. It would be good to know what exactly.
Yeah. So let's say you. I mean, so for instance, these like what I like to call strong data processing inequalities, which are versions of this inequality where you just have like a constant over here, so something that does not depend on the particular state. right? That you have on the other side of the inequality.
Yeah.
And then you as you know well, you can then like say that if you apply the quantum channel many times, then the relative entropy will like decay exponentially on how often you apply the channel or something like that. And if you had an inequality like this one, you could also maybe say more about you could get more refined versions of the statement, saying like, oh, like if your initial state had that and that property, then you would converge faster or slower or things like that. For instance, that's something I had in mind.
Right. So convergence in relative entropy sort of questions.
For instance, yeah.
Okay.
Okay. Thanks for presenting the problem. You can see if there are some more questions. Oh, thought we hit something. I saw in the chat David Suter mentioned yes, but they don't include any recovery map. I don't know. David, do you want to?
This was just a response for Joe's question. So Joe was mentioning that like strong data processing inequalities have been studied, obviously by classical people, like Alswede and Doboshin and many others. I'm not an expert, but and then there was, okay, as far as I read Joe's question, the question was, okay, what is this different now? And I think the difference is that here Daniel wants to have some dependence on the recovery map, which I think is a really nice question, but I have no clue how one does it or how it would look like, but sounds very intriguing.
Yes, exactly. So yeah, as David correctly pointed out, now and I should mention this, of course, people have studied these strong data processing inequalities at length, but I think what would be nice is to really have something which has this state dependency in terms of this recovery map. So that's exactly a nice point, yeah. Okay. Good. Then there aren't any other comments or questions. I'll stop sharing.
Yeah, I think.
A second. Stop sharing it. Cool.
We could check the Slack, but I think there's no. And then, yeah, thank you, Daniel, for presenting the problem. And we have one more speaker who announced that he has an open problem. And then I remind you that you can also spontaneously just drop in after this. And yeah, we have Alvaro. If you just want to share your screen. Or,
yes. Let me see if I can do it. Oh, I have an error. Oh no, hang on. Oh, sorry, I'm having a technical problem apparently. I'm sorry. Okay, is that, am I sharing now?
I think so. It's loading for me.
Okay, great. Okay, so I guess I have a problem on a bit of a different topic, which I mean, the hope is that we can sort of relate it to things that people in this community think about. And it's about tensor networks, which is maybe not something you sort of work on with in your daily life, but I mean, hopefully you still find the question interesting. So actually, I would say, well, it's about the relation between tensor networks and the Renyi entropies and divergences and possibly communication protocols. So I would say there's already a result, an important result in which the Renyi entropies appeared in the context of tensor networks, and I mean, you can see it in this paper by Bestrat and Chirac, and it's basically telling you when you can approximate a particular a pure quantum state in one dimension by a matrix product state of a certain bond dimension, with bond dimension measuring the complexity of the state. And the result is just something like this simple inequality. So you have the norm between your state and some other state. And in this case, what happens here is that I cut the Schmidt, the vectors in the Schmidt decomposition up to a number d. So I have a reduced Schmidt rank in this state. And the error in doing this is basically given by the Renyi entanglement entropy. And importantly, the alpha parameter has to be smaller between 0 and 1, basically. And essentially, this tells me is that if my state has, for instance, an area law of entanglement, this will be a constant. And I only need a bond dimension, which is something like 1 over epsilon or something like this. So this is nice, and this is actually very simple to prove, no? But I guess what I want is something, well, basically to extend this to mixed states, okay? And maybe to have a similar expression for mixed states, no? So what I would like to see is something like the following, no? So some bound, so a result that tells me that some bound on the Renyi mutual information, I don't know which type of Renyi and which type of mutual information, no? Because there seems to be a few, no? Implies that there's a good approximation to a particular mixed state by a so-called matrix product density operator, no? Which is just the generalization of a matrix product state to operators, no? So well, I guess I have a more explicit conjecture of what this could look like, no? And it's the following. So I will have the one norm difference between my state that I want to approximate and a particular MPDO that I am guaranteed that it exists, no? And this is upper bounded by something that looks a bit like this one, no? Which will be the exponential of a mutual information, and in this case, I'm writing the max mutual information, no? Defined with the Dmax, no? With the largest possible Renyi divergence, as far as I understand, no? And then here you again have the log D, no? So you have to maybe understand this expression as taking the limit of alpha goes to 0 here somehow. And in this slide, I've defined the mutual information in this way, but you can also define it maybe differently. No, I think in the previous talk, the way it appeared in the problem was with an optimization over the marginal over B here. No, so that this will also be fine. This will also be fine. So, something of this form. I mean, this is very vague, and something like this maybe doesn't hold, but maybe something in the spirit of this. No, I don't really know. Okay, so why this? So I guess we have a little bit of evidence for this, no? And this is what I want, what I want to say now. So one point of important evidence is that this thing that I'm showing here somehow collapses to the right in the right limit to the case of pure states, no? And the reason for this is, I guess, it's taken from a little result by the book of Katri and Wilde. Is that this definition of the mutual information that I'm telling you upper bounds the Renyi zero entanglement entropy. So so if this is not too large, then this is not too large. So my state can be approximated by an MPS. And also another point of evidence is actually in this paper, which is a lightning talk in this conference presented by Samuel Scarlett. This is something we were working on at Max Planck. And it's basically saying that you have a thermal state in one dimension, which are states that we know are well approximated by MPOs, not by MPDOs. Actually, this is I'm not sure this is known. Then this quantity actually has an area law. So this quantity is upper bounded by a constant. So this guarantees that you can approximate it by a tensor network. No? And of course, this quantity, this mutual information appears in many communication and hypothesis testing scenarios. No, as you know much better than me. No. So what is the hope? No. So first of all, let me just say something about this matrix product density operator. No. So there's a particular way in which you can write this. Sorry, and this is not general. Well, you can see it in this paper, but also in others. And I just took this as an example because this is also where this picture comes from. And you can think of it as, you have your initial site, no, and then you have a quantum channel which has two outputs, no, and one of the outputs is the physical leg, and the other output is the virtual leg, no, and the virtual leg has dimension which is equal to the one dimension. No? So somehow, if you apply this channeling sequence, you achieve an MPDO, no. So what's happening here is that you basically so you can think of this as a channel that goes from A1 to C1 here, no? So there's some sort of maybe, this maybe looks a bit like some communication scenarios, no? So maybe a particular hope, which I don't know if it's true or not. Maybe people that know more about the technical details of these things can tell me more, no? But we really didn't know, no? We tried to work on this a bit, but we weren't sure where to look exactly, no? It's whether you can cast this way of building an MPDO as a communication protocol of some kind, no? Maybe something like a reverse-Shannon theorem or like a state redistribution. I don't really know. So a communication protocol between adjacent parties where the communication cost is related to the max mutual information that I said earlier. It could also be another one. No? I'm just saying the max because it seems to be the one that maybe is more promising. No? And in doing so, maybe you achieve basically, you have a way of building the MPDO that has to do with the max mutual information, and maybe in doing so, you achieve something like this inequality here. No? So this is very vague. I don't know if this works. No. So if someone can tell me whether there's a nice reason why it doesn't, then please do so. And also, if you think that this can work also, please also tell me. And here's my email if you have any more questions. So yeah, thanks.
Okay, thanks a lot. Do you have any questions or comments on this open problem?
Hi, Alvaro. It's Nilanjana here. Just a question in the very first inequality that you showed with the pure states. Is it, I've not seen this before, so is it evident as to what is the optimal alpha in the right-hand side?
No, so it's kind of, no, so the point is that whenever you have a particular state, this side here, then presumably you can calculate the entanglement entropy for some alpha, no? And then this alpha is the one you plug into the expression, no? I guess ideally you want the alpha to be as small as possible, I think. That's the better bound, no? As small as possible. But sometimes you cannot. Sometimes you have maybe alpha equals 1/2, no? So, yeah.
Okay.
But
so
then
it depends on calculating the first term, right? The Renyi entanglement entropy, right? That's the one you calculate.
Yeah, this is what you have to calculate. Yeah.
Thanks.
Yeah.
Okay. Any other comments? Otherwise, we are already at the end of the pre-planned part of the program. So there's one last chance if anyone wants to drop in with an unannounced spontaneous open problem. I guess that's not the case. And yeah, then the only thing left is to thank again all three speakers for sharing their open problems with us. And yeah, I think we can just stop at this point. Hope you all enjoy the rest of the conference and see you around.
Thanks, Christoph.
Bye.
As I'm already here, could I maybe just use 1 or 2 minutes to try to share my iPad screen, as it did not work before, and I was planning to use it for my talk tomorrow? Would that be okay?
For me too. Go ahead.
So it said something about using a cable. Let me see if it works.